Okay, so let's begin. First of all, I want to say congratulations. You all survived the exam. Well, you don't have your grades back, but you completed it. So yeah, I just want to say, so we're going to have the grades back as soon as we can. The CAs are all busy grading, and we're actually going to cancel office hours today so we can focus on getting those grades back to you quickly. After this, the course definitely goes downhill, so you guys can kind of like take a breath. So after the exam, there's pretty much just two things left. So there's the project. So the final presentation, the poster session for the project is going to be, I believe, the Tuesday after vacation. It's like a big auditorium hall. There's going to be a lot of people from industry and academia. It's really exciting to have so many smart people showing off their hard work. And then you have the last P set, which is logic. Yeah. Oh, Monday. Okay, yeah. So right after you get back from vacation is that poster session. And then on Thursday is the last piece that is due, logic. So logic is, so this is not like my official opinion, but I think logic, when I took the class, was easier than the others. It doesn't take as much time, so you guys are definitely past the hardest point in this class. Yeah, I think that's the general opinion, yeah. But that being said, I wouldn't wait until the last minute. Still start early. And okay, so then, yeah, so Piazza and office hours will be your best friend, yeah. Okay, so but today, though, we're talking about this fun, advanced-ish topic, which is deep learning. I say ish because I think a lot of you are probably working on deep learning or have heard of it already. A lot of you have it in your projects. And today, we're just kind of do a very, very high level broad pass of a lot of different subjects within deep learning. Hopefully get you excited, give you kind of like a shallow understanding of a lot of different topics so that if you want to take follow-up classes like 224N or 229 even, then you'll be armed with some kind of background knowledge. Okay, so first we're going to talk about the history. So deep learning, you've probably heard of it. It's really big, especially in the last 5-10 years, but it's actually been around for a long time. So even back to the 40s, there's this era where people are trying to build more computational neuroscience models. They noticed that they knew back then that there's neurons in the brain and they're arranged in these networks. And they know that intelligence arises from these small parts. And so they really wanted to model that. The first people to really do this were McCulloch and Pitts. So Pitts was actually a logician. And it was, they were concerned with making these kind of like logical circuits out of a network-like topology. Like what kind of logical expressions can we implement with a network? Back then, this was all just a mathematical model. Like there was no backpropagation, there were no parameters, there was no inference. It was just trying to write about like theorems and proofs about what kind of problems these structures can solve. And then Hebb came along about 10 years later and started moving things in the direction of, I guess, like training these networks. He noticed that if two cells are firing a lot together, then they should have some kind of connection that is strong. This was inspired by observations. So there's actually no formal math theory backing this. A lot of it was just very smart people making conjecture. And then it wasn't until the 60s so neural networks was, I guess you could say maybe in the mainstream, like a lot of people were thinking about it and excited about it until 1969, when McKinsey and Popper, they released this very famous book called Perceptrons, which was this like big fat book of proofs. And they were basically talking about they proved a bunch of theorems that were about the limits of very shallow neural networks. So for example, early, I think very, very early in this class, we talked about the XOR example, where if you have two classes and they're arranged in this configuration, then there's no there's no linear classification boundary that you can use to separate them and classify them correctly. And so McKinsey Pepper, in their book Perceptrons, they came up with a lot of these, I guess you could say like counterexamples, like that, a lot of theorems that really proved that these thin neural networks couldn't really do a lot. And at the time, it was a little bit of a killing blow to neural network research. So mainstream AI became much more logical, and neural networks were pushed very much into, I guess, a minority group. So there's all these people thinking about it and working on it, but the mainstream AI went definitely towards kind of the symbolic, logic-based methods that Percy's been talking about the last couple of weeks. But like I said, there's still these people in the background working on it. So for example, in 1974, Rubos, he came up with this idea of backpropagation that we learned about, using the chain rule to automatically update weights in order to improve predictions. And then later on, so Hinton and Rumelhart and Williams, they kind of, I guess you could say, they popularized this. So they definitely, I guess you could say, rediscovered Rubos's findings, and they really said, oh, hey, everybody, you can use backpropagation. And it's a mathematically well-founded way of training these like deep neural networks. And then in the 80s, so today we're going to talk about two types of neural networks: convolutional neural networks and recurrent neural networks. And the convolutional networks trace back to the 80s. So there's this neocognitron that was invented by a Japanese Fukushima, and it kind of laid out the architecture for a CNN, but there was no way of training it. And in the actual paper, they used hand-tuned weights. They were like, oh, hey, there's this architecture you can use, and basically we just, like, by trial and error, came up with these numbers to plug in it, and look at how it works. Now it just seems like insane. But back then, that was this, there were no ways of training these things. Until LeCun came about 10 years later. And so he applied those ideas of backpropagation to CNNs. And LeCun actually came up with so there's the LeCun net, which was a very famous check reading system. And it was one of the first industrial large-scale applications of deep learning. So whenever you write a check and have your bank read it, almost all the time there's a machine learning model that reads that check for you. And those check reading systems are some of the oldest machine learning models that have been used at scale. And then later, so recurrent neural networks came in the 90s. So Edelman kind of proposed it, and then there's this problem with training it that we'll talk about later, called exploding or vanishing gradients. And then Horrieder and Schumbritter, about 10 years later, came up with, I guess you could say, maybe it solved to some extent those issues with a long short-term memory network, LSTM. And we'll talk about that later. And then, but I guess you could still say that neural networks were kind of in the minority. So in the 80s, you used a lot of rule-based AI. In the 90s, people were all about support vector machines and inventing new kernels. If you remember, support vector machine is basically just like it's a linear classifier with the hinge loss, and a kernel is a way of projecting data into kind of like a non-linear subspace. But in the 2000s, people finally started making progress. So Hinton had this cool idea of, hey, we can train these deep networks one layer at a time. So we'll pre-train one layer, and then we'll pre-train a second layer and stack that on, third layer, stack that on, and you can build up these successive representations. And then deep learning kind of became a thing. So this looks like maybe 3-4 years ago, it really started taking off, and ever since then, it's really been in the mainstream. And you can, as kind of proof, evidence towards its mainstreamness, you can look at all of these applications. So speech recognition. For about almost a decade, this performance in speech recognition, state-of-the-art recognizers were using a hidden Markov model based, that was the heart of these algorithms. And for 10 years, performance just stagnated. And then all of a sudden, neural networks came around and dropped that performance. And what's maybe most surprising is that all of the big companies, so IBM, Google, Microsoft, they all switched over from these classical speech recognizers into fully end-to-end neural network-based recognizers very quickly in a matter of years. And when these large companies are operating at scale and they've dozens, maybe hundreds of people have tuned these systems very intricately. And for them to so quickly and so radically shift the core technology behind this product really speaks to its power. Same thing with object recognition. So there's this ImageNet competition, which goes on every year, that says basically like how well can you say what's in a picture. And so for years, people use these handcrafted features. And all of a sudden, AlexNet was proposed, and it almost got half the error of the next best submission for this competition. And then ever since then, people have been using neural networks. And now, if you want to do computer vision, you kind of have to use these CNNs. It's just the default. If you walk into a conference, every single poster is going to have a CNN in it. Same thing with Go. So Google DeepMind had a CNN-based algorithm they trained with reinforcement learning, and it beat the world champion in this very difficult game. And then in 2017, it did even better. It didn't even need like real data; it just did self-play. And machine translation. So Google Translate for almost a decade had been working on building a very, very advanced and very well-performing classical machine translation system. And then all of a sudden, the first machine translation system was proposed in like 2014, 2015. And then about a year later, they threw away almost a decade of work on this system and transferred entirely to a completely new algorithm, which again speaks to its power. But what is, I guess, deep learning? Like why is this thing so powerful, and why is it so good? And I think, so broadly speaking, it's a way of learning, of taking data. You can slurp up any kind of data you want, like a sequence, a picture, even vectors, or even like a game like Go, and you can turn it into a vector. And this vector is going to be a dense representation of whatever information is captured by that data. And this is very powerful because these vectors are compositional. And you can use these components, these modules of your deep learning system, kind of like Lego blocks. You can, concatenate vectors and add them together and use this to modify you. And just the compositionality makes it very flexible. Okay, so today we're going to talk about feed-forward networks, convolutional networks, which work on images, or I guess just anything with repeated kind of like structural information in it. Recurrent neural networks, which operate over sequences. And then if we have time, we'll get to some unsupervised learning topics. Okay, so first for feed-forward networks. So in the very beginning of this class, we talked about linear predictors. Linear predictor, if you remember, is basically you define like a vector, W, that's your weights, and then you hit it with some input, and you dot them together, and that just gives you your output. And neural networks, we define very similarly. So you can think of each of these hidden units as the result of a linear predictor in a way. So working backwards, you define a vector W, and you hit it with some activation function, with some activation like inputs, some hidden inputs, and you dot that with your hidden, and you get your output. And then you arrive with your hidden by defining a vector and hitting it with inputs. So you use your inputs to compute hidden numbers, and then you use your hidden numbers to compute your final output. So in a way, you're kind of like, I guess, stacking linear predictors. Like each number, so h1, h2, and f of theta are all the product. I guess you could say they're all the result of like a little mini linear predictor. They're all kind of like roped together. So just to visualize this, if we want to go deeper, you just rinse and repeat. So you could say this is a one-layer neural network. It's what we were talking about before with linear predictor. You have your vector weights, and you apply it to your inputs. For a two-layer, you apply, instead of a vector to your inputs, you apply a matrix to your inputs, which gives you a new vector. And then you dot this intermediate vector, this hidden vector, with another set of weights. And that gives you your final output. And then you can just rinse and repeat. So you pass through a vector, you pass through a matrix to get a new vector, you pass that through another matrix to get a new vector, and then you finally, at the very end, dot it with a vector to get a single number. So just a word about depth. That's one of the reasons why these things are really powerful. So there's a lot of interpretations for why depth is helpful, and why kind of like stacking these matrices works well. One way to think about it is that it learns representations of the input, which are hierarchical. So H is going to be some kind of representation of X. H prime is going to be a slightly higher level representation of X. So for example, in a lot of image processing systems, H maybe represents, H could represent like the edges in a picture. H prime would represent like corners. H double prime could represent like small like fingers or something. H triple prime would be the whole hand. So it's successfully, I guess you could say, like just higher level representations of what's in the data you're giving it. Another way to think about it is each layer is kind of like a step in processing. And you could think of it maybe like a for loop, where it's like the more iterations you have, the more steps you have, the more depth you have, the more processing you're able to perform on the input. And then last, the deeper the network is, the more kinds of functions it can represent. And so so there's flexibility in that as well. But in general, there isn't really a good formal understanding of why depth is helpful. And I think a lot of deep learning is, there's definitely a gap between the theory and the practice. So this, I guess, just goes to show why depth is helpful. So if you input pixels, maybe your first layer is giving you edge detection, and your second layer is giving you little eyes or noses or ears, and then your third layer and above is giving you whole objects. So just to summarize, so we have these deep neural networks, and they learn hierarchical representations of the data. Successfully, I guess you could say it's like gaining altitude in its perspective. You can train them the same way that we learned. You can train them the same way that we learned how to train our linear classifiers, just with gradient descent. So you have your loss function, you take the derivative with respect to your loss, and then you propagate the gradients to step in a direction that you think would be helpful. And this optimization problem is difficult. So it's nonlinear and non-convex. But in general, we found that if you throw like a lot of data at it, a lot of compute at it, then somehow you manage. Okay, so it seems like the slides are a little out of order, but basically just to review how you train these things. In general, it's the same as a linear predictor. You define a loss function. So for example, this is squared loss, where you'd say, I'm going to take the difference between my true output and my predicted output and square that. And then the idea is to minimize this. And the way you do that is you sample data points from your training data, and you take the derivative of your parameters with respect to this, with respect to your loss function, and then you move in the opposite direction of that gradient, which would hopefully move you down on the error surface. So the problem is a non-convex optimization problem. So, for example, linear classifier, because it's linear, we'll have it'll just look like a bowl. Whereas these things, you have these nonlinear activation functions, and you end up with a very messy-looking error surface. And before the 2000s, that was the number one thing that was holding back neural networks, is that they were difficult to get working. They were hard to train. And so basically the thing that's changed is, one, way faster computers. We have GPUs, which can parallelize operations, especially those big matrix multiplications. And then there's a lot more data. That's not entirely true. So there's also a lot of other tricks that we found out recently. So for example, if you have lots of hidden units, then that can be helpful because it gives more flexibility, you could say, in the optimization. Like if you over provision, if your model has more capacity than it needs, then you can be more flexible with the kind of functions that you can learn. So we have better optimizers. So whereas SGD it'll step in the same direction by the same amount every time, we have these newer optimizers like Autograd and Atom that decide how far to move in a direction once you've decided the direction. We have dropout, which is where you noise the outputs of each hidden unit. And that makes the model more robust to its own errors, and it guards against overfitting. There's better initialization strategies. So there's things like Xavier initialization, and there's things like pre-training the model on a related data set before moving on to the data you actually care about. And then there's tricks like batch norm, which is where you ensure that the inputs to your neural network units are normally distributed. They have mean 0, standard deviation 1. And what that does is it allows you to basically take bigger step sizes. And the takeaway here is that, but in general, the optimization problem and the model architecture you define are very tightly coupled. And it's kind of a black magic to get that right balance that you need. And we're still not very good at it. Okay, so we're going to talk about convolutional neural networks now. And so these operate over images. The motivation is that, okay, so we have a picture here, right? And we want to do some kind of machine learning processing on it. We have all the tools that we need to do that. You could say, okay, each pixel is an element in a big, long vector, and then I'm just going to throw that at a matrix. But the thing is that doesn't really take advantage of the fact that there's spatial structure in this picture. So this pixel is going to be more similar to this pixel than this pixel down here. But if you pass this entire thing through a matrix, then every pixel is going to be treated uniquely and differently. And so we want to leverage that spatial structure. And the core idea is with convolutions. So convolutions, you have this thing called a filter, which is some collection of parameters. And what you do is you run your filter over the input in order to produce each output element. So for example, this filter, when applied to this upper left corner, produces this upper left corner of the output. And an application of a filter works kind of like a dot product, where you multiply all the numbers, and then you add them all up. And so how you produce these outputs is you take your filter, and you basically just slide it around in the input in order to get your output at the next layer. So this example is a little more concrete. So whereas this was a two-dimensional convolution, because we had a two-dimensional filter and we were sliding around in both dimensions, this is one-dimensional. We have a one-dimensional filter, and we slide it horizontally across. So for example, at the very left, we apply it. So 1 times 0 is 0. 0 times 1 is 1. And -1 times 2 is -2. So -2 goes in the output. And then we do the similar thing here. So we would dot product this filter with these three numbers in order to arrive at 2. One of the advantages of this is that whereas so if you had, let's say you had like 4 inputs, so this is your hidden layer. So H1, H2, H3, and H4. And then you had 4 inputs, X1, X2, X3, and X4. If you did a regular fully connected matrix layer, then every one of these is going to be connected to every one of these. And your parameters, you're going to end up with a 4x4 matrix. 1, 1, W, 1, 2, W, 1, 3, W, 1, 4, and W, 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 W. This is what your matrix is going to look like if this is your W. Because you need a weight for every one of those connections. Whereas if you're doing convolutions, it's much more efficient because there's this idea of local connectivity. So you have your 1, H2, H3, H4, X1, X2. Each hidden layer is only connected to what's called its receptive field, which is the inputs that the filter would be applied to. And in this case, we would only have 3 weights because we just have this sliding window and you apply it at each step. So A, it gives you local connectivity. B, it's much more efficient in terms of parameters. You're sharing the same parameters at different places in the input. And it gives you this cool intuition of sliding around in the input. So it's like, I have my filter of 3 things. And it gives you this good intuition of let's say this is -1, this is 100, this is 1, and this is 3. Then you can interpret this as my filter really likes whatever pattern is going on in these 3 inputs. And it doesn't like so much all the other patterns that it's picking up on. And so, you have this nice interpretation for the filters. In general, what this looks like is, so in practice, instead of 1-dimensional, 2-dimensional, they're very high-dimensional volumes. And so your filter is going to be a cube in the input space, and you're sliding it around and applying it at every place it can fit in this input. And then the reason why the output is also a volume is because you have multiple filters. So over here, for example, this blue filter is, when you slide it around in the input, it's going to give you this like plane of outputs. But then you have a second filter, this green filter, that you can also slide around the input, and that's going to give you a second dimension to your hidden states. So Andrei Karpathy has this nice demo where basically we have a 3-dimensional input, and we have 2 filters, which are like, you could think of as little cubes, and it's sliding these cubes around in the input. And every application gives you 1 output in this like 3-dimensional output volume. So this is the same picture as before, where you're sliding around cubes in order to fill in, you could say, like layers of the output. Sliding around cubes to fill in these layers of the output. Another thing people do is max pooling. So remember that interpretation of a filter as like a pattern detector. What this is saying is you take a region in your input. So you run your filters of the input, get your like preliminary output, and then you look at regions in the output and take the maximum activation and carry that on to successive layers. And the intuition there is that instead of that you're searching for a pattern in a region of the input. And it's also helpful because, remember, at the end of the day, we want to do classification or regression or something. We want to get this thing down to like a very small number of numbers. And if we have this huge high-dimensional volume, then any way we can reduce its size is good. So this is an example of how these things work. They're pretty straightforward, basically. So you just have your convolutional layers, you stack them all up. Every once in a while, you have some pooling, and you go down and down in dimensionality until you eventually get down to a distribution over possible labels. And this ties into what I was saying before about that Lego block analogy, because this entire network is built up of 1, 2, 3, 4 different Lego blocks in a way. And it's basically just stacking them on top of each other and composing them up in order to get a image classifier. So I'm going to talk about 3 case studies of CNN architectures. So the first one is AlexNet. So this was that one that did really well in the ImageNet competition and really brought CNNs to the mainstream for computer vision. Basically, it was just a really big neural network. One trick they did was they used ReLUs instead of... so the sigmoid that we've learned about, I think we've